All right, since we've talked quite a bit about regular polygons, we know a bit about central angles, interior angles, exterior angles, quite a bit with that. What I think I'd like to do is talk about the role of regular polygons in tessellations. And to define a tessellation, just you'll actually find this in section 14.5, but I just wanted to give you the basic idea. It's like a tiling. So, for example, a regular tessellation, you could take a regular polygon, like there's the hexagon, and it's a repeated pattern with no overlap and no space shown. So, for example, here's the regular triangle being tessellated. We just repeat it over and over again and make some nice patterns. Here's the regular quadrilateral, of course. We can see the square being tessellated. So again, the focus right now is just regular polygons, and it's a repeated pattern with no space. Now, just stop for just a minute. That's just a basic idea of tessellation. You could have many different kinds of shapes, and we can see a sort of what I call a mix and match, right? Different kinds of shapes being tessellated, a tiling pattern, very good, tessellation images, and we just see some fantastic artwork with this idea of repeated shapes being tiled or tessellated, and some wonderful kinds of art that you could look at. But what I wanted to focus on here was what is it about regular polygons, like the triangle, why does it tessellate? And what I'm asking you to focus on is the interior angles. So we know that the interior angle of a equilateral triangle is 60 degrees, and because it's 60 degrees, and that's a factor of 360, watch what I'm trying to emphasize here is the key point in a tessellation is watching the way these interior angles come together at a common vertex, and I think I can show it to you right here. So again, you're focusing on these 60-degree angles as the interior angles. Here they come. So what's so special about this is as follows. They come together right here, and you know something very, very particular about 60 degrees, interior angle, another interior angle. All these interior angles will come together to make 360. The same thing for the square, and the same thing for the hexagon. The hexagon, for example. Now, you know that the hexagon has an interior angle. We did that earlier in the week. You know that that interior angle is 120. Well, what's so special about 120? Well, it's a factor of 360. So when you start pushing these interior angles together, they're going to come together at a common vertex right here. We'll show it to you. We'll make a nice big spot right here. Common vertex, right? But what's so powerful about the regular triangle, the regular quadrilateral, the regular hexagon is those interior angles being factors of 360, 90, 90, 90. They come together to make that 360 at that common vertex. Common vertex meaning right there where the Mr. Happy smiley face is. So think about this. These three shapes, right? Equilateral triangle, regular quadrilateral, regular hexagon. Well, what about this? Now, what are we looking at? What are we looking at here? Well, we see the regular pentagon, and we're thinking, doesn't the regular pentagon tessellate? Surely this regular pentagon, it must tile all by itself, but it doesn't. Look, there's one pentagon, the other one fits. Here comes the third one, it fits, and of course I'm asking you right now to take a look at this common vertex right here, right? And think about what you know about the regular pentagon. Well, earlier in the week we could find this interior angle. I'm thinking it's 108, but we could figure that out. But I'll tell you one thing, those interior angles aren't going to come together to make 360, because here comes the other one, and you can see his interior angle. Here he comes. He wants to come join the party, but it's not going to fit. So what's the punchline? Regular pentagon does not tessellate all by itself. This is a terrible thing. We're very unhappy. And then we're thinking to ourselves, well, what about surely something like the octagon? So beautiful. The octagon must tessellate by itself. Here's one of them. Here comes another one. Now, before we go any further, think about what you know about the regular octagon. Well, for starters, you know the interior angle, or you could find it. We did it earlier in the week. So you know that this interior angle is, I'm thinking it's 135, because earlier in the week we found the central angles, we found the exterior, the sum of the interior, we've done all this. But think now, the interior angle is 135, there's another 135, and well, here comes another. It's going to look beautiful, but it won't tessellate all by itself. There's going to be some space. And here comes the other one. Now, I'm not saying it's not a beautiful pattern. What I'm saying is the octagon can't be pushed together at a common vertex. Those interior angles aren't going to work. So again, when we think about all of these regular polygons, and we did so many, look at it. Regular triangle, regular quadrilateral, regular pentagon, regular hexagon, heptagon, octagon, nonagon. So many beautiful regular polygons. But which ones are going to tessellate completely by themselves? The only ones that will do that are this guy, and this guy, because of the way their interior angles come together. None of these other ones will tessellate by themselves. So again, you can mix and match, and that's a lot of fun, make some great artwork, but it's because of the way that these interior angles join together to make 360 that makes them so special. The reason I wanted to do this with you is because this notion of a tessellation is going to pay off big time when we think about area and what constitutes a tiling. So that's something good to think about for now, and I think I will stop with that. Thank you.